Like up here with the, oh, which laptop are we using, by the way?
No idea. I'm not.
So this one is the one that's projected up there, but this one, I don't know what this is
That
for.
is the front.
Okay. Oh, it's, okay. Okay. Yes, so you already announced it, right? So they were kind of, well, actually, do you think there was an extra copy of the scoring rubric too, the score sheet?
Yeah. You have a rubric? Just in case. I have the show. Please take your seats. Please make your way to the first floor. We're going to go shortly. Hey, first floor. You said your seats, or you just
Okay, good morning, everyone. Welcome to NJIT. My name is Taha Marhaba. I'm the chair of the Civil Engineering Department. I'm pleased that we have 7 teams here with us today competing for the collegiate and the high school divisions. I welcome also those of you who are on the internet through the YouTube channel. Our first order of business is I'd like to ask Dean Moshe Khan to give the welcoming remarks. Thank you.
Thank you, Taha, and good morning, everybody. My name is Moshe Khan. I'm the Dean of the Newark College of Engineering. I wanted to tell you a little bit about the facility that you are in, and maybe we'll start a little bit with philosophy, why we built it. So we were thinking a lot about engineering education and the trends in engineering education. And of course we should, because we are a large college of engineering. In fact, in the state of New Jersey, we are the largest. It's kind of Rutgers, and as every couple of years, one is the first, one is the second. And when you look historically at the way that engineering education has changed over the years, kind of went between two extremes. One of them, which was the beginning. At the beginning, it was essentially apprenticeship based. There was very little theory. You went into a shop, there was a master, and you saw what the master did, and by and by you became your own professional. And over the year, and this is how it started. And then at one point, it moved to a completely different style. And it became kind of engineering science, especially in academia, and it was based on calculus-based physics and became very abstract and very mathematical. So we started with hands-on and apprenticeship-based, and if you go to the beginning of engineering education in this country, you can see it. This is Ohio State University, the main engineering space, about 1890. Here is Rensselaer, around 1905. It's interesting, by the way, that this very room today is a computer lab. And here is the University of Toronto. Here is the University of Nebraska. A lot of what you see here has to do with power engineering, which was one of the main businesses of ours then and also now. And here are some pictures from Newark College of Engineering around 1950, and you still see individuals spending a lot of time on hands-on activities. And by the way, you can see how they came to school, you know, usually in suit and ties and very formal. So what happened over time is that things have shifted. And one of the things that happened is that computer visualizations and computer simulations in many cases replaced hands-on experience. And computers are great. Computers allow you to do calculations, to estimate, to play with different design without having to build anything. But if you go too much in this direction, you kind of lose all connection to real life, and you basically start believing your simulations rather than believing your plans. And that's something that we wanted to fix. And so basically what you see in many places, this is a university, a lab in university which will remain nameless. It's called Mechanical Design Laboratory. You don't see any mechanical part inside. This is a computer-aided design we'll find in drafting. This is a power lab. And again, the power lab is completely, you look at screens and you write formulas. And this is a school that advertises engineering as a digital learning experience. So we wanted to move a little bit, not completely, but we wanted to move things a little bit toward experimentation, a little bit more towards hands-on experience, along with the computer visualization and simulation. And many other places had the same idea, except that we have done it in a much bigger and aggressive way. So here is the makerspace at Vassar College. And we visited all of them before we built this group of buildings, which is the building over there, which was the first one that we had, and the second one where you are here. And this is Northwestern. This is also Northwestern, students working in the so-called garage. Here is Yale. a very big and impressive makerspace, and us, the makerspace at NJIT. And this is the other building, which I hope you'll find your way into. The reason we are not there today is because of the fact that we are educating 70 individuals who come here every weekend for 20 weeks as part of an apprenticeship program that the state of New Jersey has asked NJIT to run. But it is a very well-equipped area, and you can find there, well, 3D printing, which is the business of today, but also a wood shop and a metal shop, and welding and metrology, measurements, and milling and laser cutting, and a very powerful water jet. And I hope that you'll have an opportunity to actually experience those and work there. So at NJIT, it's open to everybody. After you took a safety course, and if you want to use the machinery, you need to take specific training on the machines. And we support classes, we support groups, we support clubs, we support individuals. If you're here and you want to build something which makes sense and is reasonable in terms of the material and the time, we will help you. And of course, we are inviting other universities to work with us, and we are very glad that we have other universities here today, and high schools and middle schools. And if you like what you see, stress your teachers to have an agreement with us so that you can come here on a regular basis. And we work on corporations, and we very much are interested in groups and in individuals having ideas, talking to us, and working together towards building prototypes. One of the things that we do is competitions. So this is one. I'll show you another one, which we are going to do again next year. We have done a drone competition here. You can see some of it. I'll explain. What we did was we announced that we will open a competition using drones, and we budgeted it for 35 drones, and we had it's for 35 groups, and something like 15 drones, and 147 students came. And we gave these 147 students education in drones. They didn't know much about drones before they came here, and they worked in the makerspace. You can see them actually. And on the right, you can see the drones that they have enhanced. So basically, they use the makerspace, especially 3D printing, in order to add legs, in order to add wings, in order to enhance the basic design. And then we had the competition. You see a drone sitting there ready to fly. On the left top, you see the obstacles. So the drone had to fly and come back alive. And you'll be surprised how many were not able to make it, how many got themselves hanging on it, how many of them just flew immediately into the fence and tried to break it. About half of the drones survived it. And those that survived it, we said, okay, let's do something even more challenging. And we gave them the payload on the left top, which is fresh eggs in this contraption there. And then they flew through these again. And again, about half of them made it, which indicated that the design was stable, that the design actually met the requirements. And you can see at the end, everybody shining there with happiness. The importance for us as a school was that they built all these drones here, and that these individuals, by and large, knew very little about drones before they started. So I want to tell you something about your competition, because I thought a little bit about it. And I was thinking, what kind of technology are you guys dealing with? So you're dealing with bridges, right? And we don't know when the first bridge was built, right? But this is technology, we're talking thousands of years, right? And some of them are actually still standing. Here's one that stands one of the oldest arch bridges in existence. And this is 13th century BCE, okay? Now go to the other side of zero, to the 13th century, to the Common Era, or AD, if you may. And here is a bridge in Britain. I showed you in the map there where in Britain, if you're interested. And this was built in the 13th century. And you can see cars driving on it, okay? This thing still stands. And here is one in Isfahan, Iran, built during the Safavid dynasty. We don't know exactly when, but we know that it was between 1500 and around 1700. And here is the one which is the longest bridge in the world. I don't know if you knew that, but this is the longest bridge in the world. It is in China, the Danyang Kushan Grand Bridge, and it is merely 100 miles long. So this is technology which spans thousands of years. And how about 3D printing? So if you go to the Wikipedia page, and they'll tell you that 3D printing go back to 1800s. It doesn't go back to the 1800s. 3D printing go back to 1980. The first time that someone actually built something that you could use was 1980. And in fact, the first time that someone sold something that you could buy was what you see down there in 1992. And in fact, it was this company happens to be 3D Systems that had the first commercial printing machine, a stereolithographic machine, of the kind of which we have here. And this is the latest model, which allows you to do much more in terms of the kind of powders, including metal. And our makerspace, by the way, is able to do metal and does metal. We have metal printers. So here you are, bridging technologies that go back to, well, at least 13 centuries before the Common Era, and things that are really recent. I'm very glad we had the opportunity to do this. We'll do it again in a larger scale and based on what we will learn today. I'd like to thank the Civil Engineering Department for organizing that. I'm sure I will not be able to thank everybody who deserves thanks, but certainly their leadership, certainly their technical crew, certainly their very active industrial advisory board. I would like to thank the Makerspace crew who made this thing happen. And all of you and your advisors and yourself for doing this. I'm looking forward to see what kind of great ideas you bring in order to bridge these two very ancient and very recent technologies. Thank you.
Now I'd like to ask Mr. Rocco Palmieri, the chair of our Industrial Advisory Board, to say a few words.
Thank you, Dr. Marhaba, Dean Kam, and good morning, everyone. My name is Rocco Palmieri, and I am the chairman of the Civil and Environmental Engineering Industrial Advisory Board here at NJIT. On behalf of my colleagues on the board, I welcome you to NJIT and to our first annual 3D Bridge competition, Bridging the Future. We expect this to be the first of many annual competitions in the future. I know that you're all excited and ready to get started, but I'd like to take a few moments to just give you some background as to the genesis of the competition. The Civil and Industrial Advisory Board is composed of 16 professional members of the engineering community. We are all volunteers, and we are appointed by the college provost, Dr. Fadi Deek. We are charged to serve and support the Civil Engineering Department and to enhance student growth and development, both in their years here at NJIT and also as they begin their professional careers. The idea for the 3D printed bridge competition was first proposed by two of our IAB members, Dr. Wei Wang, PE of Urban Tech, president of Urban Tech, and by David Good, PE, who is a principal with Muser Rutledge Consulting Engineers. They proposed the concept a little over 1 year ago, and as a way to highlight the use of 3D technology, which is growing in importance in our field, constructing structures rapidly by minimizing waste in a way that mimics biology. Additionally, the event was proposed as a way to promote the use and capabilities of our makerspace facilities. And the 3D format that we chose also allowed for the inclusion of high schools in the competition, which was of extreme importance to our board members. The IAB members embraced the idea and encouraged Way and David to develop the program. Utilizing resources at NJIT, Urban Tech, and Muser Rutledge, and with the guidance and leadership of Dr. Marhaba and with Dr. William Pennock, and with the assistance of Valerie, Nasser, Steve, and Sylvana on the NJIT staff, and Whittier, Kevin, Mike and Lou Way at Urban Tech, the project moved ahead at amazing speed. And here we are in our makerspace facility, ready to undertake our very first competition. We also thank all of the staff here at Makerspace for the help and assistance that they gave us. We are all part of NJIT history today. I welcome the teams from our competing schools and thank them for participating. Our college teams, New Jersey Institute of Technology, Princeton University, and Stevens Institute of Technology. And our high schools, Applied Technology High School of Paramus, Middlesex County Academy for Science, Mathematics, and Engineering Technologies of Edison, and STEM Innovation Academy of the Oranges from South Orange. We are truly impressed with the talent of our competitors, and we are especially excited to have the three high schools competing in our event. It will be interesting to see how intimidating the high schools are with our college teams. So please keep the trash talk to a minimum. And lastly, I want to thank our esteemed judges for their participation today. They will determine the winners of the first John A. Roebling Award. I encourage all of our students who are here today to pursue your studies in engineering. One of the personal benefits of being a member of our Industrial Advisory Board is the opportunity for me to be directly involved with the students here at NJIT in many ways, and to see how bright and innovative they are. The students here today, you students here today, will be the engineers of tomorrow. You will have the opportunity to take a leadership role in developing solutions to address the problems and challenges of the future. Society needs you. On behalf of the Industrial Advisory Board, the Civil Engineering Department, and NJIT, thank you all for coming today, and please enjoy your day on our NJIT campus. Let the games begin. And I would like to bring up Dr. William Pennock, Associate Professor in our Civil Engineering Department and the faculty leader for this event.
Morning, everyone. Thank you, Rocco. As Rocco mentioned, the impetus for this competition came from two of our Industrial Advisory Board members, Wei Wong and Dave Good from Urban Tech and Muser Rutledge. And I was talking with Dave Good the other day, and he made a really good analogy for our competition. He brought my attention to the first collegiate football game ever played. It was played right here in New Jersey in 1869 between what is now Princeton University and Rutgers University. And at that time, the rules of football were not very well established. Football, American football, has its roots in the sport that became association football or soccer and rugby. And so the first football game actually looked a lot like soccer, but with a lot of physical contact. It was a pretty rough sport. And it turns out that they played with something that was like a soccer ball. So it looked like nothing like our current version of American football. This is our first time running this 3D printed bridge competition. Again, this is starting right here in New Jersey. And so I'm here to explain the rules, and this is the first of what we hope will become future iterations of what we hope will become a beloved sport among our institutions, our high schools and our universities. So we've put a lot of care into this, but we expect that we will learn from this competition and that the rules will evolve. But what we've put a particular emphasis upon this round is on the load and deflection of a simple center span static load that these bridges will face. So we've developed this load frame. It was designed over at Urban Tech, and our own Nasser Chanui took on the valiant effort of welding and bolting this masterpiece together. We are going to be putting on loads in 10 kilogram increments, and we're going to, at 100 kilograms, measure the deflection with those string potentiometers you see on the top. I'll explain that more later, but that is the crux of the competition. That's fairly objective. We have a couple of subjective criteria that you'll be held to, and that's what we're going to work on in the next piece, where we're going to look at the aesthetics of the bridges. This is independent of color. If you happen to print in multiple different colors, no need to fear. We like the variety, but the overall bridge design, as you know, the American Society of Civil Engineers, perhaps you don't know this, publishes regularly high quality photos of bridges. They're one of the touchstones of our profession, civil engineering, and they're inspiring really to just about everybody. So aesthetics will be a component of that, along with the presentation that you'll be giving on your bridge, which will be limited to 5 minutes, and the judges will hold you to that. Besides those, you'll also be building your bridge together. One of the highlights of the steel bridge competition that the colleges compete in, and that we used as inspiration for this one, is that the teams not only design and fabricate the bridge, but on the day of, they come together and assemble it as fast as they possibly can. Obviously, with a bridge that's 2 feet long, a little of the drama isn't there, but we want to keep the spirit of teamwork, and so you'll be working with your groups to assemble this as quickly as possible. Besides that, we've also taken into account the support materials that you've used. So we originally thought about basing our scoring on bridge mass or print time, but in consultation with the makerspace, one of the exciting things about 3D printing is that it minimizes waste. So this is a future direction for our profession, civil engineering. There was an article that came out recently that ground is about to be broken in Texas for the first 3D printed housing development. And I was talking with Dave Good about this as well. And one of the beautiful things about additive manufacturing is that it's a very low waste process, and it's efficient. It does what's needed without a lot of wasted effort or time, and especially materials. So we've held you to try and minimize the materials that you've put in support of your pieces. And I think a lot of you have done that. You've kept flat pieces generally oriented on the plate when you printed. Only a few teams sent me their calculation of the support material, so I had to do that calculation on my own. So if you have any disputes with it, do let us know. But I think they're probably fairly accurate, and that's a simple ranking. So without further ado, I'll just say that first Rutgers-Princeton football game ended with the Rutgers team winning. It was a close game, and the Rutgers team physically chased the Princeton team back to their campus. I hope that we can maintain a cordial and collegial atmosphere here. There's no need for that. In fact, I hope that we'll be seeing all of you again and more. After this competition is over, this is not over for us. We want to continue to develop this. Just as football went from being tackle soccer to now, a multi-billion-dollar industry in the United States. We maybe won't make billions off of this, but we do want this to become a national and even international form of competition, and we want it to start here. So we hope that we'll be in contact with you, that not only for the next iteration of this competition, but as we develop the rules, as we work with your teams to evaluate what went wrong, what could go better. We hope that you'll be in contact with us. I've really enjoyed being in contact with a number of you as we've gotten this done. So our next step then is to go upstairs. Before lunch, we are going to have the presentations, inspection, and assembly on the second floor. So let's go.
Okay, well, the abutments are the hardest part, but they're critical. Oh no, I was like, are we gonna get chased out of Newark?
Not by us.
Okay, that's good, that's good. Take it easy, take it easy.
Inside.
Wanna go back to the other one? That one has a lot, like, I'm worried about what the bendage is at.
Have to take it out, Sandy, you're doing that now?
Yeah, yeah.
Yeah, actually, you know,
Happen in, okay.
The load's gonna be more important.
Yeah, yeah. You the exacto knife? The exacto knife. Woo! Over there's the exacto knife.
Like a snap.
Careful, Warren. You're like, go away from you, not towards you. Okay.
Okay. James.
Echo?
What?
There?
Yeah. Yeah.
I think that might be the better option than letting it be.
All right, already got it.
Okay, it's okay. Just focus on getting the
Makes
next.
6 minutes. Is it all right?
Find out if we have better pliers.
Yeah, they,
Okay.
The Ultimaker failed us. Oh
they're
no.
better. Yeah. Not that they, oh. Pliers,
Okay. That's okay.
It's got
Sorry.
we got it. Okay, good.
Okay, okay.
You can, with a broken part, you can glue it.
Yes, you can glue the part, you just need glue the bridge together.
Right.
Oh.
Oh, okay.
But you're just replacing the part, that's good. And you won't get a penalty.
Yeah, we have these.
You're not the first team that has to glue.
Try.
We didn't break it. All right, buddy. We get, you want the glue?
Well, when you get done, you'll have time to be able to process the rest.
Okay. Okay. That's okay. lateral ties and the cones are over there. Is it the same side?
It's a compression connection anyway.
Yeah.
Tell us when you're done.
Place the cone,
Not
Mike?
gonna time the glue. Minutes, 15 seconds.
It looks really pretty.
Yeah. It's in the- We're gonna need glue.
Is this?
It'll work. They just need the glue though.
Dr. Crowe,
Yeah. It's not on the arches. There you go.
Yeah. Guys, can you leave anything on the tape?
Yeah. Yeah, we'll zero it first. Yep, all right,
You're
zero.
good.
Yes.
Okay, 466. 466. 0.46.
A nice light bridge.
Yeah.
Yeah. Oh, I'm sorry.
Yeah.
So are we okay to?
0.1. The other one I have. Yeah.
Okay.
So 0.986.
Oh, at least I did my thing. I hope. That's small. That's such a small.
Let's be in front of.
I'll just stop.
Well, it's not, not too poor.
Huh?
It's good, right?
This cable? Here. Is this the same one out there? No, this is one.
It's good, not too poor.
Huh?
It's good, right?
This cable? Here. Is this the same one out there? No, this is one.
It's good, not too poor.
Huh?
It's good, right?
This cable? Here. Is this the same one out there? No, this is one.
It's good, not too poor.
Huh?
It's good, right?
This cable? Here. Is this the same one out there? No, this is one.
It's good, not too poor.
Huh?
It's good, right?
This cable? Here. Is this the same one out there? No, this is one.
It's good, not too poor.
Huh?
It's good, right?
This cable? Here. Is this the same one out there? No, this is one.
It's good, not too poor.
Huh?
It's good, right?
This cable? Here. Is this the same one out there? No, this is one.
It's good, not too poor.
Huh?
It's
This cable? Here. Is this the same one out there? No, this is one.
good, not too poor.
Huh? This cable? Here. Is this the same one out there? No, this is one. Huh? This cable? Here. Is this the same one out there? No, this is one. Huh? This cable? Here. Is this the same one out there? No, this is one. Huh? This cable? Here. Is this the same one out there? No, this is one. Huh? This cable? Here. Is this the same one out there? No, this is one. Huh? This cable? Here. Is this the same one out there? No, this is one. Huh? This
Remember the red? Is the famous one. Wow. Yeah, they're getting both community. Yeah. Pretty cool. Yeah. Wait, is that one? Isn't it upstairs? Upstairs? And it's not, though. Is it? What room is that in? That does not look like anything. It has a blue floor. I think that's upstairs. Upstairs. This is bad. Oh, this is the stream. No.
You had it. I'm getting a black screen. I got a preview. Oh. Let's see what you're saying. Over here. That's not working. There I got so. No, it's a built-in image. Saved in. No, I didn't. But what's camera? You need to come upstairs. No, I mean the big this one. Yeah. We were supposed to use the USB-C. Yeah, yeah, yeah. Working. Yeah, and we're gonna try and see if we can get it. I'm just trying to get this. Try. Let's see if we can get USB-C.
Yeah, we have to see because we weren't able to pull video through this GoPro. No, it wouldn't just output, or at least we tried it with the other hub, and we're trying it this way.
That's power. Oh, okay, I'm sorry, Dustin, I'm talking about. Oh, it's in What's the board? Possible to record we're gonna try. Okay, awesome. I don't know if it would even be possible. The cool thing would be if we could show replays after, but if that's not possible, I understand. Yeah. Of course, we're putting on there, we'll record it like the SD card, so yeah. Okay, yeah, and that would be great. You can always just have fun. We could even back in the highlight. Yeah, that'd be good. Now, okay, so I'm going to be putting how the bridges are deflecting, how they're bending as well on my computer. What's the best way for me to project my computer? Yeah. So just put it on the podium basically? Yep. And then pick up the podium laptop? Okay. Okay. I wonder if maybe I could do wireless because we are limited by the, you know what, those might be long. Nice.
Put it on there.
I'm in stick. Yeah. What? Try. Power supply's over there. What? Yeah, there's one upstairs. Well, you worked the other day for us. It was actually working the other day. Yeah, I mean, it was working earlier today. Yeah.
No, I just saw that.
What? Put it out. That's it. Don't worry about the remote for now. I have one right here.
Exchange, work.
Yeah.
We have it.
Yeah. See it? Yeah.
Yeah, we have it.
Yeah, take that. Yeah. I don't have it now. Probably us moving it to the.
Like to get it on.
Yes. Yeah. Uh, I lost it again.
Very top.
Where?
Could have a longer cable coming out.
It's
Yeah,
just
this cable.
you want to switch them? Yeah. No. Yeah, you're fine. Yeah,
batteries are.
I can't get it to fix it. I can't get. Yeah, we have micro USB. Like,
Yes. Hey. Oh, you need to okay, I don't have So I think it was just to make sure that. Yeah.
And then what about the,
Thank you.
What's that? Present owners? So I'm gonna be watching them on here.
that on?
Yeah.
On, or-
Did you think you hooked up the podium or keep it at this? Yeah, I think they're centered, but these are a little. So you want to make sure there's. And once they're vertical on the bridge, just put them on, and then I'll zero and we'll put it up there.
In terms of, okay,
Which one? Let's see. Let me see, actually, this is. I want to make sure I'm doing this right.
no, yeah. So the record.
That was all that was left.
You're not setting.
So what did the teams do?
They're gonna, so the teams are gonna send 2 volunteers if they're willing. On loading.
Okay, that didn't happen.
We're gonna get the judges' inspection, so they're gonna big bomb. Yeah, listen, but yeah, we're gonna get them gloves and they can pick them up.
Alright, so that's, you got it?
You want to turn this up?
Yeah, right, yeah, I'll get on this side so I'm out of the way of this more. Yeah, that should be okay.
What's that? Oh, so
It's kind of annoying, right?
Oh,
Oh yeah, safety glasses for everyone. And is that yeah. Okay. You all have safety glasses. Okay. Are you gonna? Oh, yeah. All right, I will do that. We go. What's that? Oh, that's the mic, sure.
So, actually, you can talk about it.
Hey, are you mic?
I think it's over there.
So be able to. Yeah. Yes. So I was just I started on bucket for a second, so that you can like. Okay, perfect. Thank you. Put this together real fast.
And we got the. It's like standard baseball running.
Oh, you want to do seven?
No. But we get the price.
Yeah, we'll do that. Yeah, of course. Okay, hello?
Hello. Take your seats. We're about to get started. So I hope everyone had a good lunch. Everybody set. So, now.
And I guess there are just a few key points I want to make.
First is that this is going to be the judges. So we want to see today. We want to make sure that this is safe. There are two things going on here. One is that we're applying 10 kilogram increments onto this current one. And an important aspect of this for every team who's doing this is that there's a match to each of these plates. You only have to alternate. So the match needs to go on this way, so it's ready from the front side, and then the next side is applied this from the back side. So the reason we want these matches to alternate is so that there's not one continuous notch that can apply the race, because that will mean that they're crashing down on someone, they don't want that. So we want this to be a safer and as safe as possible. The other thing that we need to observe is that everyone looking at this is wearing safety glasses, so we can use it. And because these are plastic videos, they actually have a good area in the suit during the plates that are put on it. It's great place to have it's a good Japanese. So I think it's going to be safety glasses who's working with this. So we got the teams to send in 2 volunteers to give them the judges to work. The judges can work the teams to do it. To hold the rivers, we're going to ask is that 15 seconds between each successive roll. The reason for that is that we don't this is something that the teacher and structural course of the difference between static and dynamic elements. Test the withstand static loads. So do you have the or the guides to them that's having extra stresses that you didn't need to design for. So we want to make sure that you load these gently, slowly, so with at least 10 to 15 seconds between each one applied. So again, the judges are going to help oversee this and make sure that we do safely and slowly, but I wanted to make sure that everyone is aware so we have a good culture around this. We did run a test and we broke one basically as quickly as possible, and that was not the smart thing to do. So here we want to do it nice and slow. So we've had a few fabrication challenges with some of the high school teams that we're working out. Everyone did a fantastic job, but there's just issues with some parts. So we're going to do the college first, even though we said we were going to alternate college and high school. So we're going to follow the same order, but we're going to do all the collegiate teams first, and then we're going to do the high school teams. So let's see. So put us next. Valor? So who's next? Who are we going to call up? Okay, so we'll just go down the row then. So we're going to have Stevens come up first for their loading. One thing I neglected to mention, in the original rules, we said that we were going to measure the deflection at 227 kilograms, or about 500 pounds. We no longer believe that all the bridges will be able to make it there. So we've dropped it down to 100 kilograms. That's still a high target, and so not everybody will make it to the deflection calculation, but we hope a number of you will. So we're going to stop at 100 kilograms to make sure that we can get the deflection and prove which bridge was the stiffest. We have 10 kilograms aluminum piece at the makerspace with the water jet itself. So the weight that there was also another 7 on top of that. So
Thank you. Stevens is ready. You want some? You need a mic? I have a mic.
Six in total.
Hold on, hold on, hold on.
Seven kilograms.
Technical difficulties. Hold on. What? Oh, Wi-Fi. Need the Wi-Fi connection. Wi-Fi. Let me.
Still at 7 kilograms. There is no failure seen at this point. The bridge is doing remarkably well.
Yeah. Announcing the teams. I don't need to. Working. Okay. All right. Okay. I think we're back in good. Before I announce that. Yeah.
Yeah, just, yeah, you got,
We're
you got it.
back in business. Okay.
So the function is 0.075 millimeters.
All right, let's add 10 kilo.
The 10 kilograms
10 kilograms.
brought it down quite a bit of deflection.
All right, we have
Break it?
25 millimeters.
I'm going to, okay. Want to break it?
I think it's fun to break it, but.
Okay.
Yeah.
Okay, go ahead. Just, yeah, we're gonna. Okay. All right. You're gonna go find everybody else too. Okay.
Nice and slow.
Nice. Okay.
Bringing it up to 20 kilogram loading.
Oh.
So we have a total of 27 kilograms loading.
Yep. Okay. You want to add another one?
So it's actually still stabilizing.
Since if you can stabilize it gently, yeah.
Slowly,
So that's 31.95 millimeters.
And we're up to 37 kilograms.
I wish we had more bolts in there. Yeah, I remember.
So if we can get that to stabilize. Yeah, because I want to get the reading.
Yeah, strength potentiometers are actually helping us out.
That's right.
Back. Exploit found.
Okay. What's deflection?
And 37 kilogram loading.
All right.
Get me drunk.
47 kilograms of loading.
I say blank.
If you can, yeah. But yeah, don't get your fingers underneath. Yeah, yeah.
47 kilograms loading.
Yeah. Ready for the new one?
Let me just 58.4 millimeters deflection. 58.4. Hang on.
Max deflection. Did you get the max deflection? It's the catenary action. This is actually called the catenary action. You have two ends anchored. The deck works almost like a cable structure. You see, it deflects like a cable.
Is 50 a failure?
Yeah.
Okay, Princeton.
Yeah. You got this, Rich? Well, that's one can do. That's how we did. Okay, great. You have that. Now you can help them.
The bridge.
Yeah, that's the bridge. Oh, you're putting the problem. Okay, yeah.
Hello.
I know. You wanna practice? Yeah.
Cut the other way. Yeah.
Okay, now we're at 7 kilograms loading. And it's holding.
Ready? Okay. So for 10 seconds to 15 seconds. Okay, you load. Okay. All right, we're ready. Load. What?
Yep.
Yeah.
We didn't zero it, so it's at 0.02, but it's basically zero. We're measuring afterward. Yep.
All right, 7 to-
Mhm.
All right, load.
Yeah, so it's at 0.02, but that's just basically zero.
Okay, now we're at 17 kilograms loading.
9, 10, 11, 12, load.
Hold
Oh, hold on. Here, get the-
1.8 millimeters of deflection. Not quite see there.
Keep your fingers out from underneath.
Do I have to wear the gloves?
27 kilograms loaded.
The fingers are too long. Yeah, they got cut on. Yeah, I got it. Okay.
Function is 3.4 millimeters.
Okay.
Is someone watching the bridge for signs of distress? We need a judge watching the bridge for signs of distress.
37 kilograms loading.
That noise in the weights.
Thank you. Yeah, this will be easier for me to judge too.
Hold on.
We are 3.1 millimeters of deflection.
Okay, go ahead.
Okay.
37 kilograms loading. And some cracking sounds.
Oh. Do you know?
Hold.
6.97 millimeters of deflection.
Oh.
57 kilograms loading.
That's how nerve wracking it is, yeah.
Continuing to settle.
Some cracking noises.
Oh. The projection. Hold it together.
It could be the 5 phone, which would be the best.
That's what I'm.
That's what I'm hoping.
57 kilograms loading.
It's currently at 8 millimeters of deflection. It's slowly creeping. So your discretion whether to keep loading.
If, 0.8 millimeters, put another way up. Slow down, okay, slow.
I don't know my toes right now.
67 kilograms loading.
I hear it.
I think it's just raining outside.
Yeah, it's just raining.
Someone's cooking it up.
Oh.
Some cracking sounds at 67 kilograms loading.
Is it going through the deck?
Really? Yeah, it is bending.
Yeah.
Oh, yeah, the deck is cracking.
Oh
Well, it's just it's going through the deck, right?
Okay.
We had a problem with the thing wasn't perfect, but probably not.
no. I didn't see it.
Looks like, it's still straight, so what's the measurement?
Okay, I'll get that.
Yeah.
It's continuing to creep,
Yeah?
but it's 12.5 millimeters.
10.3 millimeters.
Oh,
We
we have smaller weights.
So 1 kilogram, 3 kilograms, 4.
I think we go to 10, right?
Okay, so, take.
We're gonna go big or go home.
Yeah.
Let's do another
You
cut.
gotta come back. Another cat.
Yeah, another 10 minutes, okay.
Just put all the rest on right now. Yeah, it's 200.
All right,
So 67 kilograms.
okay, this is low.
77 kilograms loading and more cracking.
I think it's cracking now.
Oh, it's definitely the center. Oh,
Keep going.
it's going.
16 millimeters of deflection and nothing.
Yeah. No, it's just question.
This is the inside joke. No, I told you, you may have a shear problem.
Climbing up to 18 millimeters.
Okay, so you guys want to, yeah, let's record that. 18, do you want this for the smaller weight now?
We're at 77 kilograms.
It's up to y'all. Yeah, why don't we try to go? Yeah, let's go with the 10, yeah.
Which one's the 10?
This
This right here? The squares? Okay.
real slow, Chris, real slow.
87 kilograms loading.
You want me to continue loading? I think I got it down. Yeah, I think I got it.
This is going good. I'm just surprised that it's eating into
It's
it.
the thing. It's perfect. I'm so.
Oh, wow.
Yeah.
So 25 millimeters of deflection. 20.5 millimeters.
This is the one motor failure that we can.
So what's the decision?
Yeah, why not? Yeah.
I mean, we could.
You want to do? Like a, you want to go for the 10?
Okay,
Yeah,
we're
that's fine.
we're at 87 kilograms,
What do you need to ask?
going for another 10.
There will be an.
Could be exciting. $97.
I did this here the day.
It was, and it was artwork that printed kind of funny, ended up being the part that broke.
Yeah.
Very nice.
Yeah, thanks.
Well, job well done.
Thank you.
Now we can blame the print, not our connection.
We're happy with that.
Yeah, that's the best result.
Yeah, we take one.
And if we get one with us too.
Definitely.
Hey, we get some portables, let's take one.
I just.
Yeah, with us though.
Okay, you want to be in the back or you?
That's fine. Thank you. Yeah. Okay, what, did James Moore, you want to sit on that side?
Yeah, and
We'll make it around it.
We good. You on this side? Sorry. Yeah, I'll look for here. Particularly like. I want to go to Chris, we're gonna get through that. Yeah. Oh, yeah.
It's a local job.
I think it's really good at that low.
Great job with 97 kilograms loading.
I already took this. Oh, yeah.
Yes. Are we getting chased out of here?
What's that?
Are we getting chased out? What's wrong?
Yeah, records don't show up, so they left out history at this point. Yeah.
Yeah, that's. So, oh, sure.
You're getting breath. like, they're
Ready?
Yeah.
All right. NJIT. Okay, up next.
The next team is NJIT.
Oh, it's not.
Yeah. All fine. I don't know.
Yeah.
Really? Thought it was, they measured right on the top, 75. So. Huh. Oh dear, squeeze. Oh, yeah, okay. So if we just kind of push it up and over. Yeah, look, I think it does qualify. I think it's just, it's just basically at an angle. Yeah. All right. Was it case? Hybrid. All right. Yeah, we got a sensor. Yep. All right. Yeah. Oh, it's 1, 2. You want blows? Sure, absolutely. There you go, of course. And who's loading for NJIT? Good one? Okay, so. You got gloves? Okay, good. Got gloves? Oh, really? Okay. You try, but okay. We had one team member who was, they were too big for it. Oh, yeah, okay. One size is not fit all.
No, the other one is, how about the other one? Is that the orange?
Yeah. We do have these. I don't know if they're gonna be any better. Okay.
Keep your fingers.
Yeah, you gotta keep them.
Can I go to the next one?
Okay, now is this, okay. So it's centered here?
Yeah.
Good, so that one looks centered? Because the way. Okay, good, yeah, we just wanna have nice vertical straight, okay, good. Put it down, put it on and leave line. Yeah, this thing was swinging a bit. Yeah, yeah.
Okay, we're up to 7 kilogram loading.
Go ahead. Yeah. Okay. When you're ready. Okay, Will, you ready? Let me just zero one more time. Okay. We're
We're ready.
Yeah.
17 kilograms loading.
Well, 0.405 millimeters of deflection. Well, 0.41, 0.41.
Okay.
$27 kilograms of loading.
Or 0.89 millimeters of deflection.
Okay. Go ahead.
$47 kilograms loading.
Or 1.06 millimeters of deflection. 1.07.
$47 kilograms.
It's oscillating a little bit, but
We have 1.38 millimeters of deflection.
$57 kilograms.
We have 1.75 millimeters of deflection.
$67 kilograms.
We have 2.06 millimeters of deflection.
$77 kilograms.
We'll have 2.39 millimeters of deflection.
$87 kilograms.
We have 2.7 millimeters of deflection.
$97 kilograms.
No problem.
We'll have 3.02 millimeters of deflection.
$107 kilograms.
We'll have 3.38 millimeters of deflection.
$117 kilograms.
We'll have 3.77 millimeters of deflection.
We're gonna go to failure.
$127 kilograms. And a catastrophic failure.
Local fair. That's a local fair.
$3.77.
Okay. I don't know what transfer that. How he did it, how do they, what do they, how do they?
Innovation Academy of the Oranges, the first of the high school teams.
I think we can, we can, lower the. We can lower, can you see this one? I think, can we screw it up? And,
Yeah.
Maybe give it another inch.
it's not. May not. You have to, yeah.
No, you can go lower. Yeah, probably. Make it two. Nice. Yeah. Okay.
You know what? Hey, hold on a second. Hold on. Maybe you can put away.
Right? As we adjusted, so that the lower surface of this bridge is out of the So what we're doing is we're trying to adjust the load frame so that when the bridge falls, it will fall a shorter distance. We're just taking safety precautions. So it's taking a little time.
This doesn't work, right? Oh, it was. Oh, okay. So you have to I mean, as long as it's zero, it's okay. As long as it's zero. Okay. So let's do the picture. What's power? Let's do that. And it's not. Oh, yeah, right, true.
Okay, Innovation Academy of the Oranges.
Yep.
And, just checking, are these all, things you want them? Like all the. Yep. They could be tiny, but go through. If you want to. Sure. Okay.
Yeah, so will you, zero it out well?
Yep. In just a moment.
Will it license,
I'm having a little trouble zeroing it. All right, just a moment. I'm gonna start that again. Okay, we're good.
And it's doing heat at 7 kilograms.
go ahead with the one that,
You don't want your fingers on the other side.
Can I help you?
It's like moving it.
So it's got a seam, so there's a rounded hole in the bottom.
Yeah, push all the way in.
Oh, yeah,
Don't let it swing.
17 kilograms.
Yeah.
Okay.
Just a moment, we need to record deflection.
Millimeters. Oh, that was like 94 millimeters. Sorry, guys.
24.
27 kilograms.
Put it down slow.
And if you can stabilize it, yeah, don't get your fingers under, but yeah, just on the side, then it's.
We have the reading. Hold on. Hold on.
4.12 millimeters of deflection.
Okay. Oh.
Seven kilograms.
Nice job.
You want to take a picture and
Sorry. What's this problem there? No. How's this fast? It's the whole thing is threaded? Okay. All that heavy? Yeah. There you go.
So, on threads.
Is that threaded?
Oh.
I don't know. It's like thread change there, man. It thing's barely moving. Right? Hard hats on. We actually thought about it, but yeah. The only reason I hard hat was
Do you want to try bending?
Oh, yeah. Really good. No, we don't. But we're still finger. Oh, yeah.
Yeah.
That does look better.
All right.
That's it.
Wow.
This is all day.
Yeah. That makes it over.
What did you?
I'll just go there.
Okay.
I will support her work. Yes. We made one ball. We made four, and that's what counts. Gotta make sure that they're, we have any better than that. Exactly. Yeah. All right.
Okay.
Ready?
Adding some bloom to the bridge.
What's the max? You're under the max, and then I'll. Yeah.
Okay, yeah, let me go ahead and do that.
Yeah.
Hello, everyone. I'm just to make a clarification on behalf of the judges. So in 3D printing, things don't go wrong all of the time. Probably one of failed prints, maybe they did spaghetti when they had. A few of them when putting the parts together have had them crack. Actually, there were a few teams that happened to, and so we've allowed teams where that happened to use glue, not to connect the bridges, but to fix those parts. And then, as I told the judges, so now what we're going to explain to is why tape is being used here. Tape is also used on this bridge. And the reason is that the connections between the two parts were sometimes not as many. So if the bridge was not even able to connect, it would simply fall apart. So these are not meant to be structural issues. The judges are taking into account that tape has been used.
But these are to make sure that when these bridges are loaded, that they're actually able to achieve at least some part of their potential to hold a load. So it's not meant in prejudice or unfairness. It's obviously better if you don't have to have tape on the bridge, but they're not tipping the balance.
Oh, is it? Everyone, good. Don't know how much of the weight can work. Maybe we cannot measure the distance. Just saying. Got it. Right. Too long. About bottom, top load.
I guess it all.
Yeah, just so everybody knows, we're having a bit of an issue that the bridge is a little too long for the assembly. So we're trying to figure out how we can crush this one anyway.
Oh, bye. It's over. Okay. I'm usually, I get it. It's nice to because I thought you were there. I need the mask. Yeah, we don't. Just the deck actually. Okay.
The arch didn't seem. Okay. And we really good. Like it's. Yeah, when they. And every time. Getting it from the depth of it. Good. Learning process, everybody learns. Yeah, we had a prototype. We're developing the rules. That's why. Yeah. Is that good? Wasn't the student. So we do design. But it's not. Here's the one. Are you changing logo? This month. That anywhere, you didn't have to. Yeah. All right. All right. All right. What? Yeah, I thought the whole had to be on the deck.
Yeah, yeah, I think that's the idea. Yeah.
I got a woman.
Okay, Robin. All right, thank you very much. Nice meeting you. Good meeting you. Right? Good meeting you.
Okay. Okay. Oh. Yeah. Maybe we could probably. The other thing I'm wondering is about the test that I had for. What's up? Outside. That's fine. So this little part of the deck and this. Yes, maybe.
So you have the else there.
You're saying that. I guess that's backwards. Know how much this?
Stairs.
No, we don't want to mess up these tables.
I don't think I will.
Okay. Arms wing. Then if you have it down like on the ground and like have it stuck up and kind of make a gas based on it. Like we could do something like that if you want to be. Yeah. It's not to make it to 100 kilograms, but. Yeah. Yeah. That's what it is. And then how are we gonna clamp it though?
I can get clamps. You can either see clamps or.
Because we have.
You know, I'll get the door and the top.
Okay, so because we have one bench that's a little too short, another one that's a little too large. So we're working on it right now so we can slowly build it up.
I take the head off. Right. While we're waiting, let me talk to the student. This is a great example of engineering working to solve a problem. We had a couple of problems with a couple of the bridges, and we were not going to say, team, go home. We said, how do we solve it? And a number of people got together and looked at what is the problem? How can we solve it? Now, we have one bridge that's too long. Okay, what do we do to fix it? And they're modifying the structure to allow the bridge still to be tested. We have another bridge that's too short. Again, what do we do from an engineering perspective to change the condition to meet the needs? That happens frequently. You go to construct, you get the design plans, and you go to the field, you have to adjust on site. That's part of engineering, so it's really important. While I have the mic, the college students, and I talked to a number of the teams, and I asked you how many were members of ASCE, and you all raised your hand. I emphasize that you need to continue post-graduation to be a member, because you'll never know where you'll network and find your next job, your next client, your next supporter, another team member from another company. Really important. The students, these high school students, engineering needs people like you. Great opportunity to consider a career and go to a school like NJIT or another school of your choice. Fantastic career. And it doesn't have to just be civil. I think that civil is pretty cool. But I worked as an electrical engineer, a mechanical engineer, an industrial engineer with a civil engineering degree. You can go all kinds of places and do all kinds of things. So consider engineering in your future. Especially engineering is looking to become more diverse. We don't have enough women. I like seeing all these young ladies here. We want to be a more diverse profession, so consider it, please. Engineering is a wonderful career. So, are we almost ready with the redesign? We're still working on the redesign. What does any of the students have any questions about engineering? Nothing? Yeah. You were a student once.
How many years does it take to get your professional engineer's license?
Great question. Everybody's familiar, a doctor has to go to medical school and get an advanced degree and then pass medical exams. The attorneys have to pass the bar. Well, engineers need to get licensed to practice. And a number of the students were telling me they were preparing for the fundamentals exam. First level of entry, you take an exam, you can take it while you're a senior. You pass that, you become an engineering training, you get your fundamentals equivalent. After 4 years of practice, you can take the professional license exam. Now, that's changing a little bit. Some states are allowing you to take the exam early, but you can't get your license until you have passed both exams and have 4 years of progressive experience, meaning you don't do the same thing every year. You have to grow and expand and learn to be a professional engineer. And that's a requirement by state. You can't offer engineering services without a license. That's fundamental. Any questions? I'm trying to kill time, guy. And I'm not going to sing and I'm not going to dance because you don't want to see that or hear it. Yes.
What is the most important skill for an engineer?
Most important skill as an engineer. I'm going to answer from my perspective. I'm going to ask some of my colleagues to jump in. I think there's several things. Number one, good technical knowledge in your area. If you're a civil engineer, understanding structures, understanding water resources, understanding those areas, transportation, whatever area you go into. But there's a couple of other things that are really important, and you've demonstrated it today, and that's to have communication skills. the ability to talk to other people and present your concepts, your ideas, like you were doing here. Communication, both written and oral, are critical to the success long-term of a professional engineer. Engineering ethics. I've seen example where people have done things wrong. They lost a license and they went to jail. Engineering ethics is critical to our profession. The ability to be creative and solve problems, innovation. We're seeing this right now. Be innovative. Because what's happening today, we're going to have different problems in the future. Engineers in the future have to deal with autonomous vehicles, sea level rise, climate change. Engineers know how to adapt and change their structures to meet that need, and the ability to help stop that, find ways of reducing carbon emissions and other things. So pretty broad answer. It's the technical area, it's the professional skills. And loving leadership, understanding public policy. Government decisions impact what we do. What happened recently? There was a major bill passed in the House, and President Biden just signed into law. Does anybody know what that was? What was it? Infrastructure bill. Important. We've underfunded infrastructure in the US for 50 years. I spent a good part of my career in Washington lobbying to get more money invested in infrastructure to help the public, help you, providing safe roads, safe bridges, ports that operate properly, and we're seeing the results of ports are having trouble today. There's all kinds of things. So engineers had to lobby, and lobbying isn't all bad. There's good and bad, but lobbying to get money invested in the future. Our answer in the past has always been, well, let's give you a little bit of money, patch it up. And we used to call that patch and pray. And we want to say, build it right, invest in our future. Because you look at infrastructure that was built 50 years ago, we're still using it today. So things that we build today, we'll be using into the future. How do we make it more effective? How do we make it more sustainable? Sustainability is a big piece of this too. So a lot is happening there. So things are changing. Things are changing here. Any other questions? Are we almost set? Okay, we're doing another consulting opportunity. Yeah, I mentioned ethics. I've seen some examples where people have, there was a water district not too far from here where they were playing games with the testing. The state would come by and test water to make sure it was safe for you to drink. And they were playing games. When the state came by, they had a tainted well. They shut that well off. So when the state came by, water was good. Meantime, the public was getting tainted water. Is that good? Was that ethical to do that? Hide the facts? It was not only unethical, it was criminal. That person who shut off that well lost his professional license and went to jail. But what harm did he cause to the public during the meantime? So I had an interesting conversation with the head of the Yale Medical School. And he said civil engineers had more to do with public health improvements in the US over the last 50 years than doctors. Is that a little surprising? Why do you think that would be? Why do you think civil engineers really impacted there?
Water quality, air quality, water quality.
Absolutely, and the major factor was water quality. Clean water has improved our health conditions better than any country in the world. People like Joe, who works in that sector and provides clean water and works with a lot of municipalities to ensure that they're getting pure water quality. That's the kind of things we do. Other thoughts, questions? What other kinds of engineers are there besides civil? chemical, mechanical. What does a mechanical engineer do? Anybody know? I think we're getting close. Anybody know what a mechanical engineer does? They fix your car?
Teacher has a saying that civil
Can you take that?
Our teacher has a saying that civil engineers build the targets that mechanical engineers like fire at.
Yeah, but mechanical engineers operate systems. I work with mechanical engineers designing robotics. Mechanical engineers designing manufacturing facilities for automation to make things more efficient. What do you think a chemical engineer does? Anybody ever thought? Some go into pharmaceutical, some go into chemical plants. I was actually offered a position years ago when I was leaving NJIT to be a facilities person for an oil refinery in Texas and one in New Jersey, providing oil to the public. What do you think an electrical engineer does? How about running a utility company to make sure you have electricity at home? Let's see, we have Orange, and what other schools do we have here? East Orange, right? Orange, and what other high school? Middlesex, right? Middlesex. Part of Middlesex is PSE&G, and part of it is New Jersey Central Power and Light. Orange is PSE&G.
And Applied Tech.
Provide electricity to you. Getting close.
And Applied Tech. They're at the
Okay. Okay, we're ready to go. If you think of other questions, the coaches are, the judges are here and other people are here. We're glad to talk to you about the profession.
So, the Plant Technology High School. So this was the bridge that was a little too short. So we had to modify the rig a bit. So this is one of the advantages of having a competition in a makerspace where we have lots of tools that we can do modifications and what have you. So hopefully for all your high school folks, you come to NJIT to and can avail yourself of this this state-of-the-art facility. Okay,
Awesome. Which school? Sorry, which Applied Tech. Applied Tech. Pepper. Okay.
Pardon me?
No,
That's fine.
wait for, yeah. Okay,
You're fine.
all right, we're ready. All right. Ready? Let's go.
Okay, 17 kilograms.
Yeah, wait until the reading. Yeah. Okay, go ahead.
27 kilograms. Thirty-seven kilograms.
Okay.
$37 kilograms.
Go ahead.
$57 kilograms.
Don't
67 kilograms and a little bit of excitement.
It's your call. Oh.
Final rating was 67 kilograms. Okay, we're going to modify the test assembly again for the one bridge that was a little too long. Unfortunately for that one, we won't be able to record deflections, but we will be able to load it up and we will be able to crush it like we've done every other one.
Hello, everyone. Hello. So I just wanted to announce that they are doing the calculation of the collegiate scores now. So I know a number of the college teams are getting antsy. So we should have the results for that soon. In parallel, of course, we're trying to load this bridge. We're going to ask, though, for this bridge, we've had to make an exception to our loading system. You see that we've taken off the top bracket. And what that means also is that we do not have a secure way to place the plexiglass. We haven't had anything remotely close to parts shooting out at people, but we don't want this to be the first time it happens. So we're going to ask that these first 2 rows here be cleared. So yeah, if you don't mind, yeah, we're going to, yeah, sorry about that.
Yes. So the judges are meeting right now, and so we'll be with you shortly, okay? So probably another 15 minutes or so. Right?
Yes.
Or no?
Yes, no, that's right. They're all muted. Yep. Hello. Thank you, Middlesex, for your contribution to this competition. If I can say a word on behalf of Middlesex, Middlesex was the team that was the most proactive throughout this competition, communicated with me early and often, was iterating through the design multiple times, working on getting it printed. And I know, so I've talked to this team, and I know that there have been a lot of all-nighters pulled. There were a number of challenges. They did all of their printing here, and so they had to remove their support material today. And that proved to be one of the challenges that they faced. But they overcame a lot of adversity to get here. So I just want to thank them for coming as well.
stand down there.
So I just want to say like maybe a minute, I won't be long. It's been for me and my parents are like urban technologies model, which is one is 3D bridge model. And so this is actually I made like 4 versions of this. This is the final version. It's pretty looks pretty strong. But at first, the first version is answer. Some steps to connect those pieces together. So basically, should take a painting first. So there's reasons to know well, it's going to take only 10 pounds. So that's not long term for the So this bridge, is training version. So I think that this bridge, like the part don't take direction, they don't take attention. So I just get like balance, like you take the best that have attention, and also parks have show kids and inside, also takes attention as well. So I think for popular is like 3 of these has a show kids and take attention. Much more approach the stronger. That's all I talked about. I'm speaking of the bridge. That's like.
I wanted to share with you the model that we had done this a couple times to see how we were going to get this to work, and we ended up coming up with a really successful model. It doesn't look like a typical bridge, but it was able to take like 150 kilos.
Yeah. It had a lot of reason, and then it's like
Did get the bridge to buckle, which was pretty neat to see, and what that really took, and I told it to some people already, was it took getting you have to transfer the load out of the deck into the truss that you're designing, because that's the whole purpose of the bridge. I've seen of these bridges a couple that were able to do that, but a lot of them failed at the deck, and you didn't really get the chance to absorb the full strength capacity of your truss. So we wanted to share this with you, so you can sort of see like our design process and how we try to do this too. It took us, I don't know, months and several different attempts and different iterations. So I would think that if any of you guys are still interested in this, look at how the bridge failed. If it failed in the deck, figure it out and get that load out of the deck and into the truss. I think that his use of these shear teeth, well, that's what I call them, was a great way to do that because it directly translated that load into the wall and into the truss. Alternatively, the first high school that went, I think that their bridge failed because of the way the actual orientation of the print, right? If they had printed it in a different direction because a 3D printer prints up, right? They might have had a lot more area to take that shear. So I would say print it again that way, put it together, and I think you're going to see double the load. I thought that this entire thing is very interesting, and I really appreciate you guys like coming and putting your best foot forward on this and trying to come up with unique designs. I thought that Princeton's design was beautiful. In the dedication that you guys have done it does not go unnoticed. So keep working at it. It's a huge learning curve with a 3D printer, but I believe, and all of us believe, that using technology is what is going to bridge us into the future. These things are getting more and more important in the industry, and it's really cool to see on a educational level this really starting to take off. So.
Thank you.
I understand that this has been a bit more of a delay than we expected. There were, of course, unexpected things that happened. So thank you all for your perseverance and ingenuity in getting all the bridges tested. We're now working to get the results, and I can say that Collegiate is almost finished. So we're just getting the names entered into the slides. We'll be announcing those winners very soon.
Hey, Pat. Can you repeat that, because I'm having.
We wanted to ask what other high school competitions you also host and what you're planning to host throughout the year.
You want to answer that?
Good question. High school competitions, we have, because of the pandemic, we had a break, but we have, we host the New Jersey Science Olympiad. Okay, so this is something we do every summer. But right now, I don't have any schedule for this coming year. But this is going to be happening every year. So hopefully you can all participate again next year. And we're all learning as we go.
And we were looking at, well, I didn't introduce myself before. I'm Pat Natal. I'm the former CEO of the American Society of Civil Engineers. I ran ASCE for 12 years. And I'm meeting with them to talk about, can we make this a national competition? So it would be nice next year or 2 years from now, having the regional competition here and having one in Kansas, one in California, and then having a national competition like we do for a number of things. We do a program called Concrete Canoe. We make canoes out of concrete and race them and test them to make sure they float. We do Steel Bridge, and NJIT has been the regional winner frequently over the last several years. Then there's a couple of other competitions that we have for students. So they're college level. There are some things we've talked about at the high school level, but they haven't done it yet. So there's some opportunities when you get to college to be part of this whole program. We're still waiting for they're adding up the high school scores as we speak. Yeah, Joe just said, what kind of competitions would the high schools like to participate in? Robotics? First Robotics is a great competition that goes on now. There was actually a robotics competition a couple of years ago where MIT, Caltech, Stanford, some of the major engineering schools in the country participated in it. And there was a little high school out of southern Arizona that competed and won. They beat all of the college schools. The thing that's interesting about it, there was actually a movie created about it, not just about that. ASE put a movie together about 7 years ago called Dream Big. It played at Liberty State Science Center, Franklin Institute, Smithsonian, and that was an aspect of it that this little high school from Arizona won the competition. It was pretty cool. But they talked about the engineering feats of the world, the Great Wall of China and how that was built and how it lasted so long. They talked about some of the creative things that engineers are doing about space travel and using drones for inspection of bridges and stuff. So there's some neat things out there, but high school students can compete with the colleges. So it could be fun. What other competitions might you think about that you would like to besides robotics, which is pretty cool? Yes. Drones? Yeah, drones. And as you saw, Moshe spoke this morning about the competition. He did that first competition here, and he's looking at making that a global competition. In fact, I said even the concrete canoe, we had a team come in from Japan. They shipped their canoe to compete. We had a lot of teams from Canada come in to compete, so it's beyond just the U.S. borders, which is pretty cool. You guys? Going to do the high school first? Okay. For us or them? Did I have high school like that?
I didn't know they had them. Okay. So she's got the lift. Oh, gotcha.
Want me to do the collegiate first?
Yeah.
I can do the collegiate.
Yeah.
Okay, let me start the collegiate awards for the various categories. Joe, would you mind grabbing the ones when I call them out? We're going to go second first. Second is top and the. Okay, the first one I'll do is presentation. In the presentation category, the number 2 team was NJIT. Come on up and get your award. Come on. The number 1 team in presentations was Princeton. Princeton, come on up. Okay, for aesthetics, number 2, NJIT. Number 9, Princeton. But take your plaque when you run back, okay? What's next? Fastest assembly time. Number 2, NJIT. Number 1, we said Gary was finished. Stevens. It took her 13 seconds. Okay, the next category is the least support material. Stevens, number 2. And in first place in this category, Princeton. Okay, now we'll do the high school division. We have one more? Oh, okay. Okay, my bad. Stiffness, number 2. Second place, Princeton. In first place for the stiffness competition, NJIT.
We're doing overall at the end. You do overall?
You overall?
No, we can do it over at the end.
Yeah, gotcha.
Hmm?
You can read it off of the screen.
Okay. Oh. Second place for presentation goes to STEM Academy of the Oranges. Congratulations. Huh?
Just do this.
Okay. Does it show up here before it goes over there?
No, this is yourself. I'll change.
Oh, okay. Perfect. Thank you. Okay. And first place for presentation goes to Academy of Science, Mathematics, and Engineering Technology. Congratulations.
Nice.
All right. And next we go to least support material. Second place goes to STEM Academy of the Oranges. Congratulations.
Congrats.
Okay. And first place for least support material goes to Academy for Sciences. STEM. Second place for fastest assembly time goes to STEM Academy of the Oranges. And first place goes to Applied Technology High School.
All right.
Oh, no problem. Best of the aesthetics. Second place goes to STEM Academy of the Oranges. And first place goes to Applied Technology High School. Stiffest bridge, second place, goes to Applied Technology High School. And first place goes to STEM Academy of the Oranges.
Well, we had an interesting challenge when we came to judging. We looked at it multiple ways, and now every category had a factor, so there was a percent for each area. And we did the calculations many times. We stepped back and looked at how the numbers came out, and we had a dilemma. We had two scores that were identical. Two teams, no matter how we calculated, tied. One happened to have 3 first place votes, one had 2, but the weighting modified the end result. We have a tie. Princeton and NJIT, full winners. Congratulations. Now we only have one trophy of each, so Princeton will take the trophy home. We'll make new trophies up for NJIT, and so we'll make that well. The printers, Princeton take the printer, and one of our judges has donated another printer to make it even. Thank you, David. So let's have the 2 championship teams for the first ever come up and get your recognition. The photos? Separately. Yeah, look, they're going to get it first. Oh, yeah. And you're not getting Trace Thomas. Well, yeah.
Okay.
Yeah. Put in the side shoulder.
Thank you so much.
Thank you.
Thank
you. Yeah.
Let's see. Okay.
Positive. Sure. Okay. Because of the tie for first place, Stevens comes up to your second. Your second place. Stevens. Good. Take all your heart.
What are you doing? You're announcing overall?
Yeah.
Oh, I thought I was announcing overall.
Go for it.
What do you want? You want to do?
Yeah, go for
Got the awards back?
it. Second place first.
Okay. So, as you all know, we had a really hard time deciding on all of the places with some of the challenges that we had, but I'm really glad everyone got to test their bridges in some way. So for second place, we decided on a Pride Tech High School.
Congratulations.
Congrats, guys.
Don't drop.
And we gave first place to STEM Academy of the Oranges.
That's it, I think. Just end it. All right, thank you all. Thank you for participating today, and special thanks to the mentors of all the teams. We appreciate all your efforts in helping the teams. It's a big effort. We realize that, and I hope we all learned from that process. I want to also thank the judges for today. Please give them a hand of applause. Thank you. Thank you for taking the time. And also special thanks on behalf of the IAB and the department to the staff that helped. Valerie, thank you for organizing this. And Nasser Shannawi for building this apparatus. And it had many challenges as well. And thanks to Silvana as well for helping out. And I'm sure I'm missing many others. But thank you all. It's been a long day, and we'll see you soon. With the certificates, please pick up your certificates before you leave. Okay, we have certificates for the mentors as well. So all the mentors, please pick up your certificates as you leave. Thank you. The printers, it's a heavy load, but
Straw, ready for it.
you want to bring the car here and just, yeah. Okay. And second place printers also for this second place. We have second place printers. Yes. Stevens has second place. NJIT and Princeton have first place, but Princeton will take it. We're gonna get NJIT one. Same thing with your award. Okay.